Now we've built up enough to get into the most important kinds of operators for quantum mechanics, which are Hermitian and unitary operators. These are things you can learn with a lot of definitions, and if you don't have a good conceptual structure for them, it's hard to keep the definitions straight. But if you learn where these definitions come from and why they're important, it's going to make a lot of work, especially in quantum mechanics, much clearer. So we're going to start with unitary, which are a lot like rotations, but with complex numbers. So U dagger times U gives me the identity matrix. Now, there's an important analogy here. Daggering is like complex conjugation, and then you have to do some other stuff like transposing because it's a matrix. But the analogy is with complex conjugation. Let's say I multiply a complex number times its complex conjugate and I get 1. That looks like the normal scalar version of this same equation. So what complex numbers with unit norm are, that must be what unitary matrices are. Unitary matrices are the analogy of complex numbers with unit norm, generalized to matrices. So this looks like an important idea. And from this, I'm going to hypothesize that the most important numbers inside that unitary matrix, its eigenvalues, all have unit norm. So I'm going to suggest that if U acts on its eigenvector and gets out an eigenvalue, that this right here is probably a number that's on the unit circle, an analogy with this. We already showed that the determinant of U has to be a number on the unit circle, and I'm going to bet that all of its eigenvalues must be as well. And let's try to prove that. So if I have this equation right here, I want to get the eigenvalue by itself. I've got to cancel out the vectors on this equation somehow. So I'm going to cancel the ket with a bra. I don't want to just put a bra on all of this, though. I need to make sure that I use the special rule about unitaries. I need to use a U dagger at some point in this. So I'm going to take the dagger of each side and move that on. So if I dagger all of this, if I dagger the left side, the ket becomes a bra and moves over here. That just means the vector got transposed and complex conjugated. This is just a mnemonic for keeping track of that. And the matrix U gets transposed and complex conjugated. And right here, the ket gets daggered into a bra, and the eigenvalue gets complex conjugated because it's just a number and we don't have to transpose that. So if I know that these two things are equal, their daggers have to be equal as well. So I'm going to put this same operator onto each side of the equation. So on the left side, I am going to have U dagger U sandwiched into the bracket. And on the right side, I am going to have lambda star and lambda. Now we get to use the unitary rule. U dagger U, our key assumption is that this is just 1 and doesn't matter. And these right here are just coefficients that pull out. So if I do that, this is just the identity matrix, doesn't matter. And I've got the bracket of the eigenvector is equal to lambda star times lambda. That's lambda squared. I have left over the bracket of the eigenvectors. These just cancel off from each side. And I get that the eigenvalue is on the unit circle. So this is key. So I told you that unitary matrices are like rotations in complex numbers. And sure enough, every one of their eigenvalues is just a rotation with a complex number, an e to the I theta. That makes sense. Fundamentally, these are matrices built out of e to the I thetas that belong on the unit circle. So if we found our analogy of complex numbers with unit norm, but in matrices, it would be really helpful to find the same things for real numbers. So I'm going to suggest that is what Hermitian matrices are going to be. That we want these to be the real numbers of matrices. Now this can be a little tricky. A matrix just built out of real numbers might have complex eigenvalues. When you try to solve the characteristic equation and do all that linear algebra plug and chug, you might get a polynomial where the roots are all complex. That might come up. Just using real numbers is not a guarantee that all the eigenvalues are going to be real. So let's see what worked for complex numbers. If a complex number is real, that means it is equal to its own complex conjugate. So by analogy, I am going to propose that Hermitian matrices are equal to their own dagger. Now, hopefully, this will produce something that lets us think of them like real numbers. So if I have this eigenvalue equation, I'm going to hope that that's real. Now again, I want to get lambda by itself. I want to clear out the other vectors here. So I'm going to take them with bras. Now the key matrix property I used over here was the fact that u dagger and u put together are equal to 1. Here, the key matrix property I'm going to have to use is that this matrix is equal to its own dagger. So rather than trying to throw in something extra, I am just going to keep one matrix in the mix. And I'm going to hit both sides with the bra of the vector. Later, we're going to want to connect this to h dagger, but we're just going to want one matrix in the mix now. So if these are just numbers, and I want to dagger both sides. I want to connect this to the dagger. Now remember, this is secretly row vector times matrix times column vector. All of these things get transposed. So the transpose distributes across the things in the product. So this cat gets transposed to the bra. this matrix gets daggered, complex conjugated and transposed. And this row vector gets transposed to the column vector. Now on the other side, my eigenvalue gets complex conjugated because I'm daggering. My ket gets transposed to a bra, and my bra gets transposed to a ket. But critically, I said that h dagger is equal to h. So this side of the equation must be equal to what I started with a while ago. This must be equal to the original setup, which is equal to what I had before I daggered anything. Now, if I connect these two parts of the equation, this is equal to that is equal to that, because the daggering made no difference on h. That is equal to that. I chain this together. I'm going to pull out this coefficient. And now the inner products of those cancel, and I have that lambda star is equal to the lambda. This is what I hypothesized earlier. This is the test for a real number. So the key takeaway here is that all Hermitian eigenvalues are real. So Hermitian and unitary are going to be important properties that you're going to use a lot in quantum mechanics. Maybe you already saw them in undergrad quantum mechanics. Maybe you saw them a little bit, but worked with the functions more than you worked with the matrices. This is what you're going to use all the time in grad quantum. And if you can think of these properties as the rules about the analogies to real numbers and the analogies to unit norm complex numbers, that's going to make a lot of your operations in quantum mechanics make a lot more sense. And we can take these connections a few steps farther into something that's going to make the Schrodinger equation make more sense.